Test. Oh, this works. Okay, hello. Welcome in Stockholm. I'm glad to be here again, and this time talking about fixing Erlang's distribution. So why do we want to fix the things? So the whole thing is, why did I start with Erlang actually? So let's start by the old Romans. I was building this device, and it's a flash device for automotive system, like a large embedded device, which is like not important for the following. But the predecessor device had lots of channels, like lots of parallel concurrent channels. But every customer wanted a different number of channels. So we thought we'd build a new version like this, have like networked device which behaves like one big device. And back then in 2007, I heard about a language that had built-in distribution. And so I tried it out. And that's how basically, that's how I got here in the beginning. And so I hear this story from many people that they hear about the transparent distribution of Erlang, and that attracts them the first time to the language. So nowadays it's also fault-tolerant scalability, but the distribution is one story that you keep hearing. But then when you actually use it in large scale, you see that there are some limitations, and then you need to work around the limitations or do something about it. And that's the rest of the talk. So the first time when we saw the limitations is when I did the port to the hard real-time operating system for small embedded systems, because for the application area, which was industrial manufacturing, like conveyor belts for like manufacturing plants, which were supposed to be controlled by a lot of these nodes talking to each other more or less reliably. So we needed basically a locality, a reliable local communication. We need less reliable communication like over longer distances. And for this, well, I have a video, so at least something is moving. The rest of the talk is more dry. So that's what we're actually controlling there. There's 15 Erlang nodes controlling an 8 meter stretch of manufacturing transport system. So this is all run by Erlang, everything. Distributed. So for this we need 15 nodes, because we want to have local I/O and save a lot of like wires running through around the manufacturing plant, because this is a major cost factor. The wires cost money, and putting them there costs even more money. So you want to have a distributed system if you want to improve something, and have local wires just to the sensors and actuators. And that's another picture of the system. So this was a research system which was shown on the CeBIT, and that was the exhibition on the CeBIT. But the final product actually should like run a real factory, and real factories can get pretty large. And we estimated that we need, like on one factory line, which was our unit of like operation, we need up to 1,000 nodes. So most of you probably know that somewhere between these 50 nodes that we're working and the 1,000 nodes we were wanting, Erlang distribution breaks. So I'm not saying when, because there's different numbers. There's been an old number which was 70 nodes. Then we heard about 200 nodes, but these were like 200 large nodes, like servers. But we have like tiny nodes. They have 200 megahertz, so they are like an old server, a very old server, not much memory. So we were supposing that it will break earlier for us. So we did not build a network and see when it breaks. We wanted to have the solution before. So how can we actually stay with the Erlang solution, or Erlang distribution, and scale up? There was one thing that was already presented here at this conference, like in the past, a result of research thing which was called SD Erlang, Scalable Distributable Erlang, Distribution Erlang. We checked it out. I talked about it already. It didn't work for us because it's mainly a solution of the namespace, the global namespace, which gives you like basically several sub-namespaces. But that was by far not enough for us, because we need to actually talk to across the whole network of the 1,000 nodes and have local communication. But we also need to have a few communication going a long way, like collecting metrics and controlling the whole system, getting it up and getting it down. So that didn't work for us. There's a thing called hidden nodes. I have one slide for that to explain it for those who don't know it. The thing is that Erlang distribution wants to have a fully connected network. So if you have n nodes, you get order of n square links in this network, TCP links. And the reason it actually wants to do this is actually the global registry. So there is high-level components of Erlang distribution who needs actually a fully connected network to make it work. And there's a way basically, when this component runs, which is the global registry, is a major basically bad guy here, it actually makes sure that you get a fully connected network. So if you connect a few nodes, it basically gets the list of nodes of all the nodes, connects them, and then connects them all together. And there's a way basically to hide it from global, and that's hidden nodes. That's why they're called hidden nodes probably, because they're hidden from the list of nodes that global cares about, the global registry, the global name registry. So you hide it, and then you can do your own. Unfortunately, you're also on your own, because then you basically just get the connections that you really make. You make a connection to a neighboring node and this neighboring node. But if you don't want to talk to the node over there, then you're on your own. You have to basically, on the application level, make sure that the information somehow trickles through your network. And everybody has to do this again, and it's like, it's a solution, but it's not so nice. So basically, that's what we're running on this 15-node system. We have them as hidden nodes, and we have application-level knowledge of our whole topology, which is in the demo case also not changing. And that's how we provide that, everything on the application level. One solution that is very often used is basically you ditch Erlang distributions. So you don't use it anymore. Or you use it only for a little thing, a little local thing, and for all the rest, for the scalable thing, you use your own TCP connections, run your own protocol, have your own data dissemination layer, which is usually tuned to your application. The sad thing about this is that everybody has a library like this. Everybody has a scalable system, has some library that actually solves the problem outside of Erlang distribution. But then we are not actually using the distributed Erlang, which in my case was the reason I actually went to Erlang initially. I mean, I have more reasons to stay, but it was the initial thing. And especially on embedded system, it's actually quite neat if you have your distribution, the data distribution thing built into the core system, because everything you build on top of it needs more resources. You need to serialize your terms, you implement protocols, it's all extra stuff. And the distribution always comes with the Erlang VM, so why not use it when you are constricted and thing. And that's why basically we come to the last point. Why not actually fix the problems in the Erlang distribution? I just put this slide in for hidden nodes for people who don't know how to use them. That's basically how you make a hidden node. You start it with a special option, and you basically can, the function that lists all your nodes has options, and you can basically say, tell me all my hidden neighbors, all the real connected nodes I'm there, and tell me about all the nodes of my fully connected network. So there's basically two parts. You have your fully connected network, your local cluster basically, and hidden nodes are just hanging off the other nodes. But you can't find out anything about the topology, like how do I get from this node to that hidden node over there? There you're on your own. So, fixing Erlang distribution. Before we fix it, we actually need to find out what's the problem. Why does it not work for everybody? The fully connected network I already mentioned, that doesn't scale because of number of connections grows with n square. And then if you want to have some keep alive traffic, the keep alive traffic at the final point, basically the keep alive signals are all your node processes at some point. because it gets keep alive. If you have a node system with 1,000 nodes, it would get keep alive messages from 1,000 other nodes. And if you lose 4 of those, then the node gets disconnected, and then it reconnects, and then you get error messages, and it's like not nice. There's another problem that all the messages you send over to another node, no matter from which process to which process, go through one TCP link. And if you send a huge message, like you have like a big Erlang term, and you want to send it over to the other side, then it goes onto the TCP connection, and everybody else has to wait with their messages until the big messages went through. This effect is called head of line blocking, because it's the message at the head of the line, which basically blocks everybody and takes forever, like the post office. Somebody at the post office needs to solve a lot of very complicated problems, and everybody else who just wants to drop their letter has to wait. Especially also the keep alive messages, which then if you send a really huge message over, then you actually can drop keep alive messages or delay them so far that you actually get errors. So this is one thing a lot of people basically had to solve. Then there are some possible concurrency issues on the higher levels, like for example, if you use RPC, if you want to use that, and I don't recommend for it, to actually do some scalable things, you will find out that all the RPC calls to one node go through one process. So you have a bottleneck there. Of course, that can be fixed, and that's higher level. And we won't take care about the higher level, like how we fix the higher level. We really want to fix the lower level, because the higher level is actually easier to fix if the lower level has some different properties. Since we ported Erlang to a hard real-time operating system, and we are kind of running hard real-time operations, it would be pretty neat if we actually could do hard real-time network connections, so we could use protocols that supply hard real-time to us between our nodes, and then have a distributed hard real-time application, because that would make our possibilities much larger. So currently we are using Erlang soft real-time and kind of crossing fingers, and actually works quite well, but we could do much more like speedier applications like a robot arm, like if you want to. Hard real-time is in manufacturing, for example, is always used if you need to synchronize several axes. So say several motors that need to run in sync and have a very detailed schedule to observe. Because if then one gets out of line, then the robot makes moves that you didn't plan for, and then basically its outline can intersect itself at some other point, which means it destroys itself usually, because it hits itself or it hits the floor, hits somebody else, whatever. Then there's also the issue of security. It would be pretty neat that if you could have like secure links between Erlang nodes, and fortunately the OTP team is already working on that, as I heard, because there is actually a project going on for a while inside the OTP team, and that's what I know that they're doing. They're looking at heterogeneous networks, so that you can actually have different types of links between two nodes and use the different types of links for different kinds of messages. Or, I think in their case, you have basically the link between some nodes is maybe encrypted, because it's like cross data center, and the link between other nodes is not encrypted, because you want the performance inside your data center. But for our application, it would be also neat if you could actually have heterogeneous links between two nodes, between the same nodes, basically one node for normal messages and one link for hard real-time messages, or one link for, it doesn't make sense to mix secure and non-secure messages, because then everybody finds a backdoor there. So yeah, bad example. There is a project going on in the OTP team to distribute global. To distribute, to scale it up, to replace it by something that scales better, a distributed hash table for the naming thing. So global registry is basically a global registry, global meaning global between all the nodes in a network, where you can actually register a process with a name or with some metadata, and then you can send a message, or you get the process ID for this process that can be somewhere else on the network, on a different node. And so I heard they're working on a distributed hash table. Please correct me if I say anything about like what the OTP team does, because I'm just hearing from the outside. I also heard at some point, that was not announced today, that there's plans to actually manage the links, because currently, once two nodes are connected with a link, the link is just kept up. It stays forever. You can shut it down manually, kind of, but it's like, by itself, it never goes down, even between hidden nodes. And often you have basically some messages between all of the nodes during the startup system, or have a rare message in a special case, but then frequent messages only between some nodes. So you could actually shut down all the links that you're not using. And there, I've heard there's something about like dynamic link management, that the distribution link goes down when there's nothing going over it, which then saves all the keep alive messages for a link that's never used. Every solution for Erlang distribution usually involves also epmd, the Erlang port mapper daemon, which is used to find the TCP port where the Erlang distribution listens on for a special node, because you can have more than one Erlang node on a system, so you actually need to know like which Erlang node on this system listens on which TCP port, and that's the use for the Erlang port mapper daemon, which provides this registry of node names to port names. So for example, if you want to have like different protocols between some nodes, then epmd should maybe know about that and tell the other node, yeah, if you want to talk to this node, actually you should use SSL, and maybe it even can like help with management of the certificates. For the embedded system, I also need a solution for epmd, because we don't have actually external processes, and epmd likes to run in the external process. So back then, I re-implemented epmd in pure Erlang, which I'm happy that is being adopted by the OTP team by now, as a potential future solution for epmd, because it's much easier to extend if it's in the Erlang code. And it's a pretty obvious application for Erlang code, like writing a server to talk to and whatever. So normally we would use Erlang for this if you would need to build something like this. And yeah, so this is there already, and much more extensible than the C code, especially after we have looked at the C code, which is kind of like collected a little bit of craft over the years, maybe. There is already support to plug in another distribution protocol, so you can actually run your own. I'm not going into the details because that's not what the talk is about. But it's actually there. It's not that well documented, so it's kind of a little bit hard to actually get it working. But you could, in theory, have SSL between Erlang nodes as a distribution link, and there's an example in the OTP tree how to do that. And there's some documentation also. But it's like not like a user manual, it's more a reference manual. You need to know what you're doing. So there's a command line option where you can plug in another protocol distribution module into the Erlang thing, and this module needs to basically implement this behavior, which is mainly the management behavior for the link. And at some point, to actually get the data over from one link to the other, you need a port driver into the Erlang VM, which normally is the internet, the network port driver is used for the distribution. But you could basically do your own port driver, implement another protocol or whatever, encrypted, non-encrypted, whatever you want, and plug it in. That's working today. So this area might need a little bit like make it easier maybe for people to plug in things, because you don't hear very often that people actually plug in their own distribution protocol. And there might be a reason for that. So since I want to fix it, I had a look at the source code in the Erlang runtime to actually find out how does it actually work, how do we get these messages transparently from one process on one node to another process on another node. So what I found is that when you send the message from a process, that in the context of the same process, it's actually serialized, and it's basically doing term to binary. So this is a simplification. It's doing the serial format for Erlang terms. It serializes the term. It puts a header in front, which is usually just a serialized tuple. And then it sends it off to the driver. And the driver is this port driver I talked about, which then has the TCP connection to the driver on the other end. So this is the other node. And as far as I could tell, I'm not 100% sure, but 95. Interestingly, the binary to term for the whole term is actually done in the context of the driver, like centralized. And when we have deserialized the thing, it's actually sent to the processes. So I would have expected that this would be actually happen in the processes also, because then could like run on all the cores. So there's a point of maybe possible optimization, but maybe somebody tells me, yeah, we tried that and it didn't work. Could be. Hmm? It works like that?
Each process deserializes.
Okay, then I read the source code wrong. Okay, I will fix the slide for the PDF. Thank you. So let's have a short look like what can everybody see what the Erlang distribution is doing. And there are two flags which you can send during compile. You can either edit the dis.c module in ERTS emulator. No, ERTS emulator, yes. Or, hello? Yeah. Or you can like set it during the compile turn options. That gives you visibility in what actually is sent over the link. So it prints out text when debug messages whenever something is going over the distribution. And I want to show you what's actually going on there, because I like to have demos, and if you're talking about something you plan to do, it's actually hard to do a demo. So oh, it switched to different resolution again. So let's get my two windows. So what I prepared already is like two distributed nodes running on this laptop, both compiled with these options. So the one is the node foo, and the other one is the node bar, as you could probably imagine. And they are connected already. If I do nodes on foo, you see it all knows about bar. So everything is in place. And what I would like to do is to send something from one shell to the other shell, and then let's see what happens in the distribution layer. So to make that easier, I register a name here. Whatever, test. Yeah, I can. One moment. Make this a little bit smaller then. No, it's maybe too small. Is that okay? Oops, that was the wrong way around. No? No, I registered foobar. Ah, yeah, okay. I registered already when I tried it out, so it's named foobar. So this shell is named foobar, except now it isn't, because I crashed it. Okay, let's register it again. No? Yeah. No, we are there. Okay, sorry about that. So now this shell is registered as the name foobar, and what we do here is we send to foobar at the node bar at Venus. And let's just send a number like 55. No, 42, of course. And that's what we get, basically. So you see that the first, the CTL thing, that's the tuple I mentioned. So that's the header of the message. So you get the sender and the target, which is foobar, and the message is 42, and the binary block here, basically the long thing, is what actually gets sent over the wire. And so, as you can see, the same thing is received on the other end, and then it gets decoded, and if I do flush here on the shell, I actually should see my 42. So let's see what's in our mailbox. Shell got 42. One other experiment we could do is we could send an atom. So you can see now in the message, you can see the atom text here. And what happens if I send the same atom again? Oh, I get a different message. Because there's a little optimization there, that if you send an atom over distribution, there's on each end of the distribution, there's an atom table. And the atom table, once you send it once, it's in the atom table, and then it only sends the index into the atom table, so it doesn't send all the atoms again, which would be a waste. So that's the reason you get a different message. That was already all of the demo, because I need to get on with it. Otherwise, I don't have time for my suggestions. So we started a little bit late. Do I get some extra? Let's make a deal. So that was the demo. So, hello? Play. Better. How could we avoid having a fully connected network? One way we could do that, actually, did I? Demo? Yeah, okay. One way we could do that is basically not have a fully connected network. Just don't have all the connections, like connect a few of the nodes, but not all. But make sure that basically you have a path through the network. But if you have a path through the network of the nodes, then actually you need to route messages. You need to route the messages from one node over several hops of other nodes to the final node. So for that, we can actually then decide how much TCP connections we want, depending on our network topology maybe, like map it to the network topology, or think about some virtual topology, or whatever. You can do lots of things when you can do message routing. The dynamic connection management can help some applications, but only some. And you can combine it with message routing. So you basically, if you have a route, if you have message routing like across your whole network, and you have like an initialization message on the beginning of your application when you start everything up, then you could like do a direct route more. And then when the dynamic, the link is basically taken down because there's no messages going on, then that saves also a lot of links between the nodes. But effectively what you need to do, what's not in the implementation at the moment, you need to forward messages that you received over the distribution to another distribution node. It should not be so hard, but they are a little bit. Actually, I'm missing slides now. Sorry about that. Did I skip a slide? Oh yeah, no. So they're upcoming. So let's not talk about the problems. How do we forward messages? Usually the way it's done is already like shown to us if you look at like an TCP/IP router or an IP router. So you get packets in, you look at the address where you want to go, you have a table, you look up in the table, and then you send it out by another link. We could do the same for Erlang distribution. So assuming we have a table in every node, which tells us which which TCP link, basically, which distribution link every other node is, then we can basically look up in the table and forward the message. And of course, the same at the initial message send. The initial message send also goes through this table because it's like in the beginning. If we would have such a table, it would need to be like built into ERTS in a low level. It needs to be accessible from the low level. You want quick lookup for the messages. What you also want to like is to be able to fill the routing table from the Erlang label. Because like the way it's configured should be accessible from the Erlang level, because everybody wants something different probably here in the routing table. So I was thinking about, but this is not determined, I was thinking about maybe we could abuse ERTS tables here, like a special ERTS table, which we use for message lookup. Sounds like a possible use, but that's still open, it's just a suggestion. And we also could use such a table for our heterogeneous link suggestions, so we can actually see for these messages, don't use the main link, use the hard real-time link, or for these messages, use the secure link, or for example, for small messages, use a different like embedded link between nodes. You could also make decisions on message size, possibly. How would we fill this message table, this routing table? One possibility is to do static routing, so you just configure it. And like I put up one example for static routing. So we don't want a fully connected network. So what's the next more easy, less connected solution? That would be a so-called hypercube. So hypercube is basically an extension of like point, line, square, cube, tesseract, the four-dimensional, and then go on and on and on. So basically you always duplicate the thing, and you can, in a hypercube of order n, you can have 2 to the power m nodes, which is plenty pretty soon. And the routing can be done basically by looking at, if you address the nodes like this, that you say basically the upper level nodes have their last bit set 1, the lower level have it 0, and so for each dimension you have 1 bit. Then if you want to go from here to there, you know you have to flip all the bits. So every time you cross such a line, you flip 1 bit. So we need to flip all 3 bits if you want to go from here to there. If you want to go from here to there, we know there's only 1 bit difference. So we only need to flip this bit, so we go over this line. That's the shortest path. So it's a very easy to make decisions how to get from one node to the other if you number them like this. That's just one suggestion which you can make. You can make a tree, you can make whatever your application demands. But what we also would like to do here is to have like networks like this. That's actually the network in the manufacturing use case looks like this, except like a very long stretch of 1,000 nodes, with like mesh things, with shortcuts from here to there, which you could put in to improve performance. And how do you actually configure this? This is kind of messy. First you have to wire all the 1,000 nodes, and then you have to write it down. And then you type it in a table, and if you make a mistake, it doesn't work. And then it's very hard to debug. So there's a way, which is there since a while, to actually discover the topology of such a network, which are called routing protocols. So this is a higher level protocol, which we can implement in Erlang, for example. And there have been some implemented in Erlang, which discovers the topology and distributes the important information of the topology to every node. So every node can basically fill their routing table with this topology information. And the way the today used routing protocols work is you actually have the whole graph topology in every node. Every node knows the whole topology of the whole graph. And you run Dijkstra's algorithm on it and find shortest path to every other node. And that's what you basically put in your routing table. So you actually get shortest path routing in arbitrary networks, as long as they're connected, of course. Like I rushed through this, you can read it up afterwards. The routing protocols used nowadays are all called link state protocols. They basically send like a certain number of a certain type of packet to all the neighbor nodes, to all the nodes they discover in their network. 10, okay. No, we're fine, okay. And in each of these nodes, basically, is information about like the other links, and so I don't want to go into that because 10 minutes. So this is a very efficient way to distribute, to discover and distribute the whole network topology of an arbitrary network. And then we can fill our routing table. And that would actually be for our manufacturing use case, we actually want to use something like this because one of the major things the customer wants is auto-configurability, because the configuration kind of sucks for these large networks. So it needs to discover itself, and it needs to repair itself. So this is done regularly. So whenever one node finds that a neighboring node goes down, it basically distributes this information again, and the graph gets fixed, and the routing table gets fixed, and so pretty soon it's pretty quickly converging. That's one of the major advantages of the link state protocols. There have been other protocols in the past which had the main disadvantage that they don't converge fast. So pretty soon you basically have new routes. That's a few variants that are used. The best one is ISIS, and there's also OSPF because the IETF, ISIS is from OSI, like the ISO people. And IETF, who does the internet protocols, wanted to have their own, so they invented OSPF, which is similar but different, and like a few years behind ISIS, which has only the disadvantage that it has like a weird name now, but it's like older than the other ISIS. So yeah, okay, I talked about routing messages as there would be no problems with that. That's the slides I wanted to have before. Routed messages have a few like problems. They can get out of order because when the routing table changes, after one message went through the graph, the next message might take another route which is faster. Like I plug in a shortcut and then like messages overtake each other. Kind of, yeah, okay, they get out of order. They can get lost. Before, if I have two nodes and I have one TCP link between the nodes and the two nodes are alive, which we constantly watch basically if they're alive, if I send a message over this TCP link and I don't get an error, I know the other end basically eventually gets the message. But if I have routing, then the message in transit is on some other node. I don't know anything about it. And if this node dies, my message is gone, while then my message is on the node. So we can lose messages now. And at least for temporary times, messages also can go in circles, especially when basically the routing table changes. Then you get one topology while the message is in transit, and then the topology changes and it goes back, and you can get temporary circles, and you don't want to have that. If that's a real problem, that depends on the routing protocol. But you might want to have a fix. Not to keep these messages forever, maybe. Then on the other hand, in the Erlang VM, we have a few invariants which everybody relies on. So all the messages between two processes, no matter if they're on the same node or on different nodes, are to be received are to basically be put in the mailbox in the order they are sent. Not between unrelated processes. It's just if I have process A and B, and A sends message 1 and then message 2, I expect if I receive just any message to get first 1 and then 2, and not the other way around. If it's unrelated processes, we don't need to care about that because they're already reordered in all kinds of weird things. And there's basically theoretically impossible to actually have an ordering on an SMP system at least. We have an additional lesser known thing which is actually only true for newer Erlang systems. I forgot which version it was. It's no longer, probably nobody has a version of Erlang running in production for which this is not true. So if you do node monitoring, you monitor your neighbor node or the connected node. And then you basically, if you monitor the node, you get node up and node down messages. So you get basically information when the node comes up and when it goes down. And it's guaranteed that all messages from this node are between the node up and node down. So there's not one stray message before the first node down, or a few leftover messages after the first, before the first node up, and a few stray messages after the last node down. So this is also something we should actually keep in the semantics. So how do we do this? We have the requirements. We need to reorder the messages because they can get out of order, but we need them in order for a pair of processes. So we need to reorder the messages between two processes. We need to detect when we lose messages, because then we need to do something, because we're not supposed to lose messages if there's no node down. I mean, if the node is down, the other node is down, I don't expect the messages to be there because the node is down. But if the message just gets lost, I need to do something different. And we probably want to drop the messages that go in circles, or have a routing protocol that can't, where this is avoided. So the last thing is pretty easy. You have like a hop count. You have an additional count in a message, and on every hop you increment it. And if it goes beyond, you decrement it, and if it goes below 0, you just throw it away. The ordering requires like actually knowledge about the sequence the messages are sent, and this is usually done with sequence numbers. That's how TCP does it, for example, for the IP messages. So what we would need is a separate counter for every pair of processes who actually communicate. And since the process is actually serialize and deserialize, as I just learned, this is done in process context. We could actually keep the table of all the other processes we communicate from one process in this process. So we need a table of counters, which basically increment for every message. And then on the reception, we actually check if they come in order. And if they don't, if basically a message comes that is like there's a gap, I keep the next message for a while and wait for the message that goes in the gap, and then I get the message first in the gap and then the other one. And that's also how you detect that the message was lost. You get a new message, which is like, you expect message 9, but you get 10. And then you wait, and 9 never arrives. So you time out, and then you know you lost the message. If you get like all the messages after you already detected a drop, basically, and you moved on with your life, basically, and then the old message suddenly said, yeah, I'm late, but I'm here, then you drop it, of course, because then you can't like insert it into the message stream. So what do we do with the message loss? I mean, the reordering is okay. I mean, it takes some computation, but it can be done. But what do we do with message loss? Because it's unexpected. The rule with the node down and node ups is basically a workaround where we can have message loss and be backward compatible. So every time we lose a message, we trigger a node down, node up. That won't scale if we lose lots of messages. So this is still only a solution for a quite reliable network, which is the case in our use case. So because I insert a node down, node up, all the messages that the node sent basically after the link is gone. So I pull the plug between two nodes, and this node goes on sending messages. So the other node gets a node down. All these messages are also lost, and then I get a node up, and then I know to get on with life. So this probably should work with every well-written distributed application that expects this behavior. We could actually optionally have a different semantics, like configurable, that we actually have a special message that, like, yeah, by the way, you didn't get the 3 last messages, so you lost a few, and then you can deal with it in the process. That would be an optional extension to that. So I think I need to rush now. What would also be nice, so if we have all these things, and we want to have a backward compatible way, but we also want to do new things where you actually don't care about, for example, message ordering. For example, if you have like request response things, and you don't care about the order of the requests arriving in order, and you have multiple requests in fly, and the request has a reference in it, and the response basically gives back the reference, then you might not care about the ordering of the whole thing. And so that would be nice if we had a few options to that we can actually make use of this loosened semantics, like That could be an option during sending in the send call, or that could be an option that's set for the process. Short thing about head of line blocking. Head of line blocking can be fixed. One way of fixing it is to, if you have a large term, you send slices of messages. And having the sequence numbers in already is half of the solution, because now I know I have the sequence number in every slice of my message, so I know which belong together. So all I need in addition is another little number, which basically tells me which part of the message it is. So in which order I need to reassemble it, basically. So we need just one more level of messages, and then we can have some scheduling that we send in little chunks, not like all in order, but like pick one of this and this and this, so send them out of order for this different so optimizations I skip. Very important, this is all paid by Litecoin, so the reason I'm up here is that we have actually budget from a new project, from the Litecoin project, so I need to mention that, so I need this 30 seconds, which is about edge computing. Hybrid gossip protocols are used there, CRDTs. It's a very interesting research project for huge edge networks, which are basically which we have, and in the framework of this project, we want to implement the thing. And there's one talk in the same room about the project, so I don't need to say anything about it, and that's my last slide.
If you can wait for coffee just a few more minutes, we could have a couple of questions. Any takers?
Why not just ditch TCP?
I never said we want only this TCP. So lack of time, I would have said basically when we can actually lose messages and they are small, we could just put a message in a UDP packet and just send it. And the long messages we keep on TCP and route them to the network. So all kinds of mixes are possible. And the main plan is to have everything as pluggable as possible, so you can like build this yourself on top of it. So it's your choice what actual protocol you use.
What about security? So if you use LSP, anyone can potentially get a node in your network. So any intruder could say, I play this part of the node, and then you route your messages. So you cannot have a kind of point-to-point security on those messages. No. So how are you going to solve that?
In the manufacturing use case, not, because it's like make everything in clear text. Because it's like that's how it's done in manufacturing nowadays.
But there might be demand not to do it like that.
It's a good question. Yeah, I think I don't have a quick answer to that.
Okay.
But it's an important question, yeah. Like, how do you have a network? Actually, you get a transitive security thing. So if you have certificates, you need to manage your certificates, and they can actually use them between the nodes, maybe.
So Erlang implementation TCP protocol might be handy in this.
Might be, or might be also too slow. I don't know. I'm open to that. I mean, we have one now, which is tested. Yeah, or actually reusing ideas from TCP on the Erlang message level, one level up, basically. Of course, if you have, you could route. If you have a router in every node, or a switch or whatever, you could actually use this to actually route through, but then you still have your scalability thing that you need lots of connections on every node. Yeah, that's... Yeah? One possibility.
I suggest we talk to the speaker over coffee, and let's thank him. Don't forget to leave feedback.